Hi dear students, welcome back to the class. So far we were discussing about the scalar product, the cross product, the properties of the scalar product and the properties of the cross product, and we done several problems using cross product and scalar product, right? In this class we are going to start a new section, and the name of the section is nothing but scalar triple product. From the name itself it suggests something. See, we have a scalar here, a triple here and product here. So this section is nothing but a section which deals with scalar, a triple quantity and a product. So we are going to discuss something related to all these three terms, and that is nothing but the scalar triple product. We know that the scalar product of any two vectors is again a vector. The cross product of any scalar product of any two vectors is again a scalar, whereas the cross product of any two vectors is a vector. But we always want to discuss, or we were discussing only about a pair of vectors, right? The scalar product of a pair of vector, the vector product of two vectors, only two vectors. But what is the case if we were discussing about three vectors? We know that there is associative property for scalar and vector product, so we can associate them, right? Now, in this section, we are going to deal with a special case. So, a special case can be defined like this. Suppose that we are provided with three vectors, say vector A, vector B and vector C. We chose three vectors because the name suggests a triple here. So far we were discussing about a pair of vectors. Even if we get a triple vectors, we can easily associate a pair from it, and we can find the cross product and scalar product respectively. And here the name suggests a triple, so we chose three vectors. Let A, B, C be any three vectors. Any three vectors. Then the scalar triple product of these three vectors is defined as vector A dot B cross C. What is that? Vector A dot vector C. See, we have three vectors in the product. Also, this is a scalar product, A dot B cross C. So, we have scalar triple product. The name suggests scalar triple products. That suggests a scalar product. We have a scalar product here. We have a triple vectors here. So this is the scalar triple product of any two vectors, any three vectors, and we can denote it as box vector A, vector B, vector C. So box vector A, vector B, vector C is nothing but the scalar triple product of A, B and C, and it is defined as vector A dot B cross C. Sometimes we also denote it like A without any commas, A, B, C. These are two notations for representing the scalar triple product of any two vectors. Now we shall evaluate, or we shall examine some of the properties of the scalar triple product. First property is that since B cross C is a vector, then the scalar triple product, which is A dot B cross C, is a scalar quantity. I think you can easily identify or understand this property very well, because we know that whenever B and C are two vectors, B cross C, see, B cross C will be a vector, right? Whenever B and C are two vectors, B cross C will definitely be a vector. Then since A is a vector, the dot product, A is also a vector, the dot product of two vectors A and B cross C will be a scalar. A dot B cross C will be a scalar. We know that the dot product of any two vectors is a scalar, since B cross C is a vector. Always remember that whenever two vectors are given, the cross product of those two vectors will definitely be a vector. So whenever B cross C is a vector and A is a vector, the dot product of A and B cross C will be a scalar. That is what we were mentioning in the first property. Coming on to the next property, if A is equal to A1i cap plus A2j cap plus A3k cap, and B is equal to B1i cap plus B2j cap plus B3k cap, and C is equal to C1i cap plus C2j cap plus C3k cap, then the scalar triple product of A, B, C is given by A dot B cross C, which is nothing but the determinant of A1 A2 A3, B1 B2 B3 and C1 C2 C3. I think you can easily derive this condition very well. Let us check or examine how we can easily derive this. Since B is equal to B1 I cap plus B2 J cap plus B3 K cap and C is equal to C1 I cap plus C2 J cap plus C3 K cap, we know that whenever two vectors B and C are given in the cross component form, the cross product of B and C can be obtained by the determinant I cap J cap K cap B1 B2 B3 C1 C2 C3, right? We know that this is nothing but I cap into B2 C3 minus B3 C2, B2 C3 minus B3 C2, right? Now minus J cap into, I think you all know how to derive or how to calculate the determinant of such a matrix. So always, if you don't know, just go back to the previous session and watch it well. This is very important. Now minus J cap into B1 C3 minus B3 C1, B1 C3 minus B3 C1 plus K cap into B1 C2 minus B2 C1, B1 C2 minus B2 C1, right? Let us erase this. So we have the cross product of two vectors given in the component form is nothing but this, right? Now we know that this is nothing but B cross C. Now we know that vector A is nothing but A1 I cap plus A2 J cap plus A3 K cap, right? Now see that A and B cross C are two vectors. B cross C is the vector this and A is the vector this, right? You can easily identify this is a scalar I cap, this is a scalar J cap, this is a scalar K cap, which is a vector A1 I, just like A1 I cap plus A2 J cap plus A3 K cap. So we can easily find the dot product of A and B cross C. A dot B cross C just by finding the product of the respective components. We know that whenever two vectors are given in the component form, we can easily find the dot product of those two vectors just by evaluating the product of the respective components and adding them all together, right? Now we shall just evaluate those calculations. That is, it is equal to, first component here is A1 and the first component here is B2 C3 minus B3 C1. So we can write A1 into B2 C3 minus B3 C2, right? Now the second component here is A2, the second component here is minus this. See, here we can have plus minus, plus into minus is nothing but minus. So the coefficient actually here is, the coefficient of J cap actually here is minus of this, right? So we have minus A2 into B1 C3 minus B3 C1. Here the second component is A2 and here the second component is minus of this. Actually the standard form is all plus, right? That is, here we can have plus into minus. So the coefficient is actually minus into this scalar. Okay. Now the third component here is A3 and here is that plus A3 into B1 C2 minus B2 C1. So we get the scalar triple product of those three vectors are just like this. This is nothing but determinant of A1, A2, A3, B1, B2, B3, C1, C2, C3. You can easily evaluate this determinant just by using the formula we were discussed in the previous class. See, we can have the determinant just like this, A1 into B2 C3 minus B3 C2. Correct. Minus A2 into this column and this row will be eliminated. B1 C3 minus B3 C1 plus A3 into this 2 will be eliminated. B1 C2 minus B2 C1. So this is nothing but this determinant. That was our second property. So always remember that whenever we are given with three vectors in the component form and we are asked to identify the scalar triple product, just do this. Just find the determinant with the first components of the first vector in the first row, components of the second vector in the second row, and components of the third vector in the third row. That is as simple as that. Now we shall move to the next property. Next most important property of scalar triple product is that scalar triple product of vectors A, B, C is equal to scalar triple product of vector C A B, it is equal to scalar triple product of vector B C A. That is, the cyclic permutation of scalar triple product doesn't make any change. I mentioned the term cyclic permutation. Why did I mention that term? You just observe that first scalar triple product is box ABC. Then this C came to the first place. That is box CAB. Then this B came to the first place, that is BCA. That's why I called this permutation as a cyclic permutation. This is a cyclic change. This come here, then this come here, then again this A comes here, we get box ABC, the first one itself, which is a cyclic change. We reached at the beginning stage after 3 permutation. That's why I called it as a cyclic permutation. Now whatever it is, we have the cyclic permutation of the scalar triple product or the box product doesn't make any change. That means that box ABC is nothing but box CAB is nothing but box BCA. We can easily verify this using the formula for finding the determinant. That is, if A is equal to A1 I cap plus A2 j cap plus A3 k cap and B is equal to B1 I cap plus B2 j cap plus B3 k cap and C is equal to C1 I cap plus C2 j cap plus C3 k cap. Then we can have box ABC is nothing but box ABC is nothing but determinant of A1, A2, A3, B1, B2, B3, C1, C2, C3, right? It is equal to, we can evaluate the next determinant, that will be there. Then we can have box CAB, we are now going to evaluate the second box product. It is nothing but determinant C1, C2, C3. The first component in the box product, the first vector in the box product is C and the components are C1, C2, C3. It must come at the first in the first row of the determinant. Then we have A, A1, A2, A3. Then here we have B, B1, B2, B3. And the last box product is box box BCA, right? Box BCA. It is equal to determinant B1, B2, B3, C1, C2, C3, A1, A2, A3, because B1 is the vector first in the first place of the box, and so that we have to return write the components B1, B2, B3 in the first row of the determinant and so on. So we get 3 determinants. On evaluating all the 3 determinants using our formula A1 into this, eliminating this row and this column, so A1 into this minus A2 into this plus A3 into last one, this into this. So after eliminating these 3 determinants, we can see that all the 3 determinants have the exactly same value. So we can say that the cyclic combination or the cyclic permutation is always possible. So always remember that whenever we are given with 3 vectors or 3 box product like this, always remember that these 3 box product are actually the same because there is a cyclic permutation is available here. Always remember that only these box product are same for cyclic change only, cyclic permutation only. If this C is transferred to here, of course we get this box product and these two are equal. But whenever this C is transferred to here, that is box product A, C, B is not equal to this because this change is not a cyclic change. Always remember that these 3 changes are allowed in the case of equal box product. That is, whenever we are given with box ABC, C must go to this first position, then these 2 positions are shifted, and after A must go to this position so that a complete cycle is formed. So the box products are equal only for the cyclic changes of the vectors. Now we shall move on to the next property. This property is actually a continuation of the previous property. In the previous property, we learned that box A, B, C is equal to what? Tell me. Yes, we can transfer this C to the first place, so it will be box C, A, B, and at the last we can transfer this B to this position, so that it will be equal to box B, C, A, and what will be the next transferring? this A should go to the first place. That is exactly what is this, and then there is a completion of cycle. That's why we are calling this a cyclic permutation. Or just remember these things. We know by definition this box product is nothing but vector A dot B cross C, right? It is equal to this cross product, this scalar triple product is nothing but vector C dot A cross B, right? And it must be equal to, this is nothing but vector B dot C cross A. Just look at this. That means that whenever we are given with a scalar triple product like this, we can interchange the cross product and dot product in two ways, which is exactly equal to the first one. Always remember that these three things are always equal. But if what happens, we are given to as vector box product of A, C, B, and it is nothing but A dot B cross C. Always remember that this thing cannot be equal to any of this thing, because this transferring is not a cyclic transferring. That is C which has a position here at the first is came to here in the second position now, which is not a cyclic transformation. According to this transformation, only possible three cyclic transformation in the box product to be equal is that these three positions. So this is not equal to any of these three products. So always remember these things. This is the this is a very important property in dealing with problems. Now we shall move to the next one. In the last property, we said that the box A, B, C is not equal to box A, C, B, right? Because this is not a cyclic transformation. But we have another interesting result here. We know that box ABC is nothing but vector A dot B cross C, right? We also know that this is very important result from the cross product. B cross C is nothing but minus C cross B. We described this in our property list. We said that the cross product is not commutative, but it satisfies this relation because sin theta is an odd function. So whenever we are returning or reversing the direction of the cross product, the sign will be reversed, plus turns to minus. That is what we learned in the properties of cross product in the previous classes. So applying that here, it will be equal to A cross minus C cross B, right? B cross C is nothing but minus C cross B by the properties of vector product. Now it is nothing but minus 1 is a scalar, so we can take it outside of the dot product. So it will become, it is also a property of the dot product, right? So it will become minus 1 into A dot C cross B, right? Now A dot C cross B is nothing but box ACB, right? It is nothing but minus box A C B. That is box A B C is nothing but minus box A C B. Since A dot C cross B is nothing but AC, box ACB, A dot B cross C is nothing but box ABC. So we can easily arrive at this conclusion that box ABC is nothing but minus box ACB. Now we shall move to the next important property. Now the next property is an interesting property regarding the box AAB. Can anyone guess what will be box AAB? Let's just take 5 seconds. Okay, if not, just do this calculation. We know that box AAB is nothing but it is equal to box BAA, because B comes to the first place. This is a cyclic transformation. So BAA, it is equal to BAA, and it is nothing but B dot A cross A, right? Now easily you can say that A cross A is nothing but 0. So it will become B dot 0, because the angle between A and A is 0, sin 0 is 0, so A cross A is 0. So B dot 0 is nothing but again 0. So box AAB is nothing but equal to 0. Now we can easily say that whatever be the vector A and B, if the first vector is equal to the second vector, then the box product will be equal to 0. This will be This is our last property in this section. So remember all these properties very well, because sometimes you may ask me to solve problems using any of these properties in your exam. So you should be aware of each and every property just like this. If you are asked to find the box product of such a thing, you should be able to easily arrive at the conclusion that this box product is 0 using the property we learned before. Always remember that all these properties are interconnected. So if you have to derive an answer from using one property, you must be able to interpret other properties in terms of the required property. So always remember that every property is interconnected. So we have to understand each and every property very well. The next important section from scalar triple product is that, or the importance of scalar triple product lies in the fact that we were able to determine whether three vectors are coplanar or not. We know that coplanar means two vectors are said to be coplanar if they lies in the same plane. We have three planes, namely xy plane, xz plane and yz plane. So whether these three vectors are lying in the same plane or not can be easily evaluated by using the property, or using the scalar triple product definition. Now coplanarity of three vectors is defined as three vectors, vector A, vector B and vector C are said to be coplanar if and only if A dot B cross C is equal to 0, which means that the box product is equal to 0. Just look into the condition. It is an if and only if condition, which means that three vectors A, B, C are said to be coplanar. Then we can say that the box product is equal to 0. Conversely, if the box product is equal to 0, then the three vectors will be coplanar. We can easily derive or prove this result very well, because suppose that three vectors A, B, C are said to be coplanar, which means that these three vectors lies in the same plane. If any of the vectors, suppose B is parallel to C, suppose if B is parallel to C, then B cross C will be 0. Then A dot B cross C will be again 0. That means that if B is parallel to C and A, B, C are lying in the same plane, then the scalar triple product is 0, which means that they are coplanar. Now suppose that B is not parallel to C. B is not parallel to C, then of course B cross C cannot be is equal to 0. But if B is not parallel to C, B cross C is a vector which is perpendicular to both B and C, right? B cross C is a vector which is perpendicular to both B and C. Since A, B, C are coplanar, a vector perpendicular to both B and C will be a vector perpendicular to A. Just suppose that vector A lies in the plane. This plane, this is X. Suppose that this is XY plane. Vector A lies in this plane. Vector B lies in this plane. Vector C lies in this plane, which means that vector A, B, C are coplanar vectors. Now B is not parallel to C. Then B cross C will be a vector perpendicular to both B and C. This is the B cross C. It is a vector perpendicular to both B and C. Just why? Because B and C lies in this plane. A vector perpendicular to both these vectors will be a vector perpendicular to this plane also. Since A is also lying in this plane, a vector perpendicular to this plane will be perpendicular to A also. So we can easily say that A dot B cross C. B cross C is a vector perpendicular to both A, B and C. Therefore, it will be perpendicular to A also. Since the dot product of two perpendicular vectors must be is equal to 0, we can say that whenever B is not parallel to C also, the dot product will be 0. That means that whenever A, B, C are three coplanar vectors, then the dot product or the box product is equal to 0. We can easily derive the converse part also. Suppose that A dot B cross C is equal to 0, then we can easily say that the three vectors A, B, C are coplanar. So that's it. Whenever we can easily always check A, B, C are said to be coplanar just by using this definition, just by using this condition, whether A dot B cross C is equal to 0 or the box product or the scalar triple product is 0 or not. If it is 0, then the ABC is said to be coplanar. If it is not 0, then definitely A, B and C are not coplanar, since it is an if and only if condition. Now we shall do several problems using these properties and these conditions. Coming on to the first question, find A dot B cross C. So we are asked to find a box product. Find A dot B cross C where vector A is equal to 2i cap plus j cap plus 3k cap. 2i cap plus j cap plus 3k cap. Vector B is equal to minus I cap plus 2j cap plus k cap, and vector C is equal to 3i cap plus j cap plus 2k cap. So we are given with three vectors. We are asked to find the box product of these three vectors. We know that whenever we are given with three vectors in the component form, we can easily find the box product of those three vectors using the formula of determinants. That is, box product A, B, C is nothing but determinant 2, 1, 3, minus 1, 2, 3, 3, 1, 2. Always try to focus on the question. A dot B cross C is asked, so A must come at the first row, B must come in the second row, and C must come in the third row. So it is equal to 2 into, we know that how to find the scalar determinant of three vectors. 2 into 4 minus 3 minus 1 into minus 2 minus 9 minus 2 minus 9 plus 3 into minus 1 minus 6 minus 1 minus 6. It is equal to 2 into 4 minus 3 is equal to 1 minus 1 into minus 2 minus 9 is equal to minus 11 plus 3 into minus 1 minus 6 is equal to minus 7. Right. It is equal to 2 minus into minus plus 11. Minus 3 into minus 7 is equal to minus 21. So 13 minus 21. Next question is, find lambda if the vectors are A is equal to, we are asked to find a scalar called lambda, and if the vectors are vector A, vector B and vector C, we are given with three vectors. A is equal to I cap plus 3j cap plus 3k cap. And vector B is equal to, I cap plus 3j cap plus k cap is the vector, and vector B is equal to 2i cap minus j cap minus k cap, and at the last vector C is equal to lambda I cap plus 7j cap plus 3k cap are coplanar. So we are given with three vectors, and given that these three vectors are coplanar, then what should be the value of A? We know that when three vectors are coplanar, then the box product A dot B cross C must be equal to 0. We can use this condition. A dot B cross C is nothing but determinant of 1, 3, 1, 1, 3, 1, 2, minus 1, minus 1, 2, minus 1, minus 1, and lambda 7, 3. Right. A dot B cross C. It is equal to, now we can evaluate the determinant using the formula of determinant 1 into minus 3 minus 3 minus 1 into minus 3 minus 3, minus 1 into 3 is minus 3 minus 7. So 1 into minus 3 minus 7 minus 3 into 6 minus lambda, 6 minus lambda, 6 minus lambda, and plus 1 into 14 minus lambda, 14 minus lambda. So it is equal to 1 into minus 3 plus 7 is nothing but 4 minus 3 into 6 plus lambda plus 1 into 14 plus lambda plus 14 plus lambda. So we can simplify this thing as 4 minus 3 into 6, 18 minus 3 lambda plus 14 plus lambda. Right. Now we can simplify this thing again. 4 minus 18 is nothing but minus 14. Minus 14 plus 14 is equal to 0. So minus 3 lambda plus lambda is equal to minus 2 lambda plus 0, and this box product must be equal to 0 for 3 vectors to be coplanar, so it must be equal to 0, which means minus 2 lambda is equal to 0, which means lambda must be equal to 0. That means lambda must be equal to 0 for these 3 vectors to be coplanar. We can you may have changed value of lambda according to the change in question. You may get lambda equal to 5, you may get lambda equal to 10, whatever, the steps are always the same. So focus in these steps. We have to find the value of lambda when this condition happens. This condition means that the box product must be equal to 0. So first we evaluated the box product and equated lambda to 0. So we can move on to the next question. Coming on to the last question from this section. This is a very important question and asked in previous year examination. So focus on this question. We have to prove this condition. Box A plus B, B plus C, C plus A is equal to 2 into box ABC. So we have to prove this. How we can prove this? Suppose that from the LHS is equal to box A plus B, B plus C, C plus A. This is our first left hand side. We can expand this using the definition of the box product. Is equal to vector A plus B dot B plus C cross C plus A, right? Because by the basic definition of box product we know that instead of this ABC, it is nothing but A dot B cross C, A dot B cross C. Now we can use, see the bracket, we can use the distributive property of cross product here, right? It is equal to A plus B into, sorry, this is dot. Now we can use the distributive property B cross C plus C cross C, B cross A plus C cross A. See, we are using the distributive property just like that. And this. So we have B cross C plus B cross A plus C cross C plus C cross A, just using the distributive property. Now we know that C cross C is equal to 0, since the angle between them is 0, sin 0 is equal to 0, so we can just eliminate this. So it will be equal to vector A plus B dot B cross C plus B cross A plus C cross A, right? Now we can evaluate the dot product as A plus B dot, A dot, this distributive property of the dot product can be used. So it will become A dot B cross C, B dot B cross A. So we can use the distributive property just like in the previous class. A into this, and A into this. Then we have B into this, B into this, not into B dot this, using the distributive property of the dot product. We shall check what happens. So first of all, A dot B cross C, A dot B cross C plus A dot B cross A, A dot B cross A. Now A dot C cross A plus A dot C cross A, right? Plus next one is B dot B cross C, B dot B cross C, okay, plus B dot B cross A, B dot B cross A, plus last one is B dot C cross A, B dot C cross A. Okay, now observe that A dot B cross C, it is box ABC, right? Box ABC. It is box ABC. Now A dot B cross A, it is box ABA. It is equal to 0. We discussed the property that whenever box ABA, it is equal to box BA, it is equal to box AAB, it is equal to box BAA. We are using the cyclic transformation. BA transformed here, then the B transformed to here to get BAA. It is equal to 0. Whenever we have such a situation, it must be equal to 0. So this is equal to 0. Again, A dot C cross A, it is equal to 0 by the same property. Again B dot B cross A, it is equal to 0 by the same property. Again it is equal to B dot B cross A, it is equal to 0 by the same property. And last one is B dot C cross A, right? It is nothing but box BCA, and by the cyclic transformation we can transform it to here, it will become ABC. So it is nothing but box ABC. It is equal to 2 into box ABC. So we reached the final answer just by applying the property. Just remember that I always said that these properties are interconnected. So we have to learn each and every property. If you know at least one, if you don't know at least one property, you will not be able to solve this problem correctly. So always remember that each and every property is important. So that's the end. I think this is clear. The scalar triple product is clear for you. Hope you understood this concept very clearly. Just rewind every concept, every section, every properties very well in order to achieve full score in your board exam. We shall discuss some complicated problems regarding this towards the end of this session, and in the next chapter we will see with three-dimensional geometry. We shall move on to the section in the next class. So stay tuned for that. Bye bye.